Good day. Today, we'll discuss measures of central tendency and dispersion. I would like to begin this discussion with a case. Today, we have seen a lot of patients admitted in the hospital for COVID-19. And so, a researcher wanted to know how long do COVID-19 patients stay in the hospital on the average. And so, he made a phone call in the different hospitals and asked for the medical records of all patients that have been admitted in these hospitals until discharge. The researcher got a total of 283 patients, and he calculated the mean hospital stay to be 22.4 days. He likewise determined the shortest hospital day to be 7 days and the longest 30 days. The researcher, however, noticed the values to be skewed, so he wanted to know as well the number of hospital days that will separate the upper half and the lower half of patients. And lastly, he wanted to know how variable the length of hospital days of patients is. And so, these are the learning objectives for today's session, that at the end, you will be able to define the three measures of central tendency, discuss and differentiate the one from each other, and then demonstrate how to calculate manually the three measures. And I would like to demonstrate to you how to calculate manually these measures so you'd be able to understand more clearly these measures. And so we'll also be discussing to you how to calculate manually measures of location or order statistics, and lastly, manually the different measures of dispersion. Let's begin with the measures of central tendency. The first is the mean. The mean is the simplest statistical procedure among all measures of central tendency. It is the most commonly used measure to summarize a set of quantitative data. When laymen talk of the average, they usually mean the mean. But I would like to believe that people really don't mean the mean when they talk of the average, because they don't normally calculate. For example, if you ask a physician, how many patients do you have on the average in a day, he will just look up the ceiling and then say, well, about 30. He doesn't calculate. So I would like to believe that when laymen talk of the average, they mean the mode. But really, technically, when we say average, we mean the mean. So let's take, for example, these numbers: 8, 14, 15, and then up to 7. And then the mean is just the sum of all the numbers divided by the total number of observations. We call that the n. And so the formula for the mean is this one: mu is equal to mu, that's the mean, is equal to the sum of x divided by n, where this one is a summation sign, sigma. And the expression tells us to add all the values in the data. Sum of x, where x is a variable, it represents a value, each value, and then divide the sum of the x's by n, where n is the number of observations in the set, and then we get the value of the mean. And so, using the values that we showed to you a while ago above, we calculate the mean to be 11. The mean is 11. You see, the mean can be likened to a fulcrum along a beam of numbers. You see, a fulcrum balances a beam, and in much the same way, we can look at the mean as the fulcrum where it balances a set of numbers. And outliers or values that are either very high or very low tend to pull the mean towards them. And so, the mean is sensitive to outliers. Now, let's go to another measure, the median. That is the middlemost number in an array. Let us take again the numbers 8, 14, 15, etc. up to 7. When we calculate or when we determine the median, we first arrange the numbers in an array. And so, we arrange the numbers from highest to lowest or from lowest to highest. We arrange the number in an array. You see, class, the median is determined rather than calculated. The median is the middlemost number in an array. In the table that we just showed to you, where n is an odd number, 9, it's easy to pick the middlemost number, 8. In a case, however, where n is even, the median is located halfway between two middle numbers. So that if n is even, there are two middle numbers. And then the median is located halfway between these two middle numbers. And so, if we add another number, 25, in the values that we showed to you a while ago, and then n now becomes 10, that's an even number, and then the median becomes the average of two middle numbers. The two middle numbers are 14 and 8, and the median is 14 plus 8, that is 22 divided by 2, and then the median is 11. So we show to you here again the median, the array, the numbers in an array. The middle numbers are 14 and 8, and the median will be halfway between these two middle numbers. So the median is 11. And so formally, we can give the definition of the median as if n cases are listed in an array, the median is the number or value at position 1/2 of n plus 1, or n plus 1 divided by 2. That number or position at n plus 1 divided by 2. And the median equals the value of the middlemost case if n is odd, and of the average of two middle values if n is even. So again, we show to you these numbers that we showed to you a while ago, where n is odd. These are 9, and 9, when we go to the formula for the location of the median, so 9 plus 1 is 10, divided by 2 is 5, and the median is at the 5th position, whether you're coming from the top or from the bottom. So from the top, the 5th number is 1, 2, 3, 4, 5. The fifth number is 8. If coming from the bottom, this is 1, 2, 3, 4, 5. So the fifth value is 8. And therefore, the median is 8. The median is 8. Now, if we add another number, 25 here, 25, and n now becomes 10, and that's an even number. So 10 plus 1 is 11 divided by 2, and that is 5.5. And so the median will be between the fifth and the sixth number, 5.5. So that's between the fifth and the sixth number. So coming from the top, the fifth number is, we have here 25, and then 2, 3, 4, 5. The fifth number is 14, and the sixth number is 8, and the median will be halfway between 14 and 8, and that's equal to 11. And so the median is 11 if we add here 25, where n is now even. Now, theoretically, the median divides a ranked list of values in halves, so that 50% of cases have values below the median, and the other 50% have values above it. And this statement is not only theoretically true, but exactly true if n is even. If n is even. A while ago, we added 25 to the set of values that we showed to you, and then we told you that the median is 11. That's between 14 and 8, and the median is 11. And if we count the numbers above 11, that is 5, and the numbers below 11 is also 5. That's exactly 50%. So that 50% of cases have values below 11, below the median, and the other 50% above it. We'll show that to you in a little while. But let me just show to you, class, that unlike the mean, the median is resistant to outliers, to extreme values. We told you that the mean is sensitive to outliers. Outliers tend to pull the mean towards them. But the median is not sensitive. It's resistant to outliers. Now, let's show to you again where this set of values where we added 25 in the table, and we told you that the median is 11 here, and the total number here is 10, and then the median is 11, and 50%, 1, 2, 3, 4, 5, 5 is 50% of 10 is above 11, and then 50%, 1, 2, 3, 4, 5, another 50% is below 11. So as I said, that statement where 50% is above the median, 50% of the values is above the median, and the other half, 50% below it, is exactly true if n is even. But if n is odd, that statement is only theoretically true. Because if n is odd, we told you that the median is 8, and the number below 8 is 4, and the number above 8 is 4. But 4 is not 50% of 9. We have here n equal to 9, where 50% of 9 is 4.5. And so I said that that is only theoretically true if n is odd. Now, we'll go to another measure called the quartiles. And quartiles divide a ranked list of values into quarters. We told you that the median divides a ranked list of values in halves, quartiles into quarters, deciles into tenths, and percentiles into hundreds. Now, the first quartile is that number, again, theoretically, greater than the values of the 25% of cases and lower than the values of the remaining 75% of cases. And so, if we have, for example, a list of values arranged in array from lowest to highest. So suppose we have here a list of values, and then this is the median, and then we divide this into 4, and then we told you that the first quartile, this is actually the first quartile, and I denote it as Q1. That's the first quartile. This first quartile will be that value that is higher than 25% of cases but lower than the rest, than the 75% of cases. And then the third quartile, Q3, and I denote that as Q3, will be that value that's higher than 75% of cases and lower than 25% of cases. The second quartile, and I denote that as Q2, will be that value that's higher than 50% of cases and lower than 50% of cases. The second quartile is also called the median. Now, the deciles divide a ranked list of values into tens. The first decile will be that value that's higher than 10% of cases and lower than 90% of cases. The fifth decile will be that value that's higher than 50% of cases and lower than 50% of cases. The fifth decile is also called the median and the second quartile. Now, percentiles divide a ranked list of values into hundreds. 5% of cases lie below the fifth percentile. And so, again, if we have this array of values, and this, for example, is the fifth percentile, and I denote this as P5, this is the fifth percentile, and this is higher than 5% of cases and lower than the 95% of cases. This is the 5th percentile, lower than 90%, 95% of cases. This is the 50th percentile, that's higher than 50% of cases and lower than 50% of cases. Class, the 50th percentile is also called the second quartile, the 5th decile, and it's also called the 50th percentile. Percentiles class can define other order statistics. The first quartile is also called the 25th percentile, the median, the 50th percentile, the third quartile, the 75th percentile, the 6th decile, the 60th percentile, the 8th decile is also called the 80th percentile. Quartiles, deciles, and percentiles, like the median, are measures of order statistics. It is called order statistics because these values, the median, quartiles, deciles, and percentiles, tell us their order or rank. So, if your grade is on the 90th percentile, your grade is higher than 90% of cases. You're only lower than 10% of cases. So it tells us its order or rank. That's why they are also called order statistics. Some people call them measures of location because they also tell us where that value is located. For example, the median is located at the middle. The third quartile is located at the 3/4 of the 3/4 higher than the rest of the values. So people call them also measures of location. And they are particularly useful in locating the rank of a certain measurement, say anthropometrics, relative to the measurement of other children of the same sex and age. And that is why pediatricians will tell us the nutritional status of an individual, of a child, for example, of a male child of the same sex and age using the percentile. If the child's weight is on the 5th percentile, so his weight is on the 5th percentile, meaning his weight is only higher than 5% of all children of the same sex and age, and his weight is lower than the majority, the 95% of children, and therefore that child is malnourished, is undernourished. Now, let's go to the last measure of dispersion, the mode. In French, le mode means the fashion. And that describes to us something that is seen most frequently. Similarly, the number that appears most frequently in a set of values or data is called the mode. If we have two modes, we call that set of value as bimodal, or we can also have more than two modes. We call that set of values as multimodal. Of course, it's possible to have a set of data where there is no mode. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there is no mode. So we call that set of data as amodal. Amodal. So we have this set of values. So the mode is 5. If we add another number, 7, the modes are 5 and 7. So that's bimodal. If we add another number, 14, the modes are 5, 7, and 14. So that's multimodal. If we add another number, 14, so we have 3 14s, and then the mode is 14. Now, let's go to the measures of dispersion. And this is also known as the measure of variability or the measure of spread. It tells us, these measures tell us how variable a set of data is, how the data are spread. So, let's try to understand the measure of dispersion by way of a case. Suppose we have two sections of a class in biostatistics that have taken the same test under the same conditions. And then we find the mean grades in both sections to be 50. So for example, section A, the mean grade is 50. In section B, the mean grade is also 50. Does that tell us that does that mean 50 tell us that the performances of the two sections in the test are similar? Well, let's look at section A. In section A, all grades were found to be between 40 and 60, and the mean is 50. In section B, however, the grades range from 0 to 100, and that include grades in the 10s, 20s, etc. And then, the mean grade is also 50. If the mean grade in both sections is 50, it seems that the performance of the two sections is similar. But if we look at these values now, we have the values that we present to you in section A and section B, and then we won't think anymore that the performances of the two sections are comparable. Clearly, the mean by itself does not provide to us a complete picture of a set of values, such as the case that we mentioned above. While the mean tells us the location of the distribution center, it says nothing about the dispersion, the variation, the spread about that center. And so, we need to understand as well measures of dispersion. We actually have 4 measures of dispersion: the range, the variance, the standard deviation, and the coefficient of variation, which I failed to write here, the coefficient of variation. And we'll discuss these different measures of dispersion one by one. First, we discuss the range. If we arrange a set of values in an array, the distance from the smallest number to the largest number is called the range. A while ago, in the set of numbers that we showed to you previously, the smallest number is 3 and the highest is 25. And so, the range is the difference between the highest, 25, and the lowest, 3, and the range is 22. Actually, there are two ways of reporting the range. We either subtract the lowest from the highest, as we did here, and then we said that the range is 22, or we just say what the lowest and what the highest numbers are. So we say that the range is 3 to 25. The range is a good measure of dispersion if values are normally distributed. But if there are outliers in a set of values, the range no longer becomes a good measure of dispersion. We go to the next measure of dispersion, the standard deviation. Now, if all the values in the data set were identical, there will be no variability. Variability only exists when two or more data in a set of values have different values. 10, 10, 10, 10, 10, 10, 10, 10, 10, 10. There are no variability. And so, the standard deviation is 0. Now, the range that we discussed above only looks at two extreme values, the lowest and the highest. It does not take into consideration other values in the set that contribute to its variability. And the standard deviation is one of the most important measure of dispersion. It is actually the cornerstone in the understanding of many concepts of statistical inference. And it takes into consideration all values in a data set when it measures the variability. And it is defined conceptually, and I would like to emphasize this conceptually, as the average deviation from the mean. Now, to understand standard deviation, let us look at this situation. Suppose there are two alternative routes from your house going to FEU and RMF. And one route, I will denote that as route A, is shorter than the other route. I denote that as route B. But travel time for both averages 30 minutes, meaning the mean travel time for both routes A and B is 30 minutes. Now, in route A, however, travel time can be as fast as 12 minutes when traffic is light and can be as slow as 60 minutes when it is heavy. In route B, however, the flow of traffic is consistent. Travel time ranges from 25 to 35 minutes. Now, suppose you are still in your house, you have an examination at 8 o'clock, you're still in your house, 7:25, which route will you take? Obviously, you don't want to take route A because by that time, 7:30, traffic is already heavy So you might want to take the route B where the flow of traffic is consistent. I mean, it's not heavy, it's not very light, but it's not heavy. So you might want to take route B. But if, for example, travel time for, if, for example, the examination is at 1 o'clock and you're still in your house at 12:30, and you know that traffic during that time is light, so you might want to take route A because you can get to FEU much faster than if you in route A than if you take route B. So you will note, class, that in route A, the standard deviation is much higher. In route B, the standard deviation is much lower. The standard deviation, class, is a measure of how variable, how consistent data are. Now, let's show to you how we calculate the standard deviation manually, so you'll be able to understand more clearly the meaning of the standard deviation. The standard deviation is computed first by taking the deviation of its value from the mean. We told you that the mean is equal to 30. And so we get the deviation of its value from the mean. And we denote that as x minus mu. Now, class, suppose I have 5 patients. And these 5 patients have ages of 1, 2, 3, 4, and 5 respectively. So I have 5 patients. Now, the mean age of my 5 patients is 3. First, class, we get the deviation of each of these values, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 from the mean. So 1 deviates from the mean by negative 2. 2 deviates from the mean by negative 1. 3 deviates from the mean by 0. 4 deviates from the mean by 1, 4 minus 3, and 5 by 2, 5 minus 3. We call these values deviations from the mean. Negative 2, negative 1, 0, 1, and 2. So these are deviations from the mean denoted by x minus mu. And we told you a while ago that the standard deviation is defined conceptually as the average deviation from the mean. So we get the average deviation from the mean. So we call this deviations from the mean, and we get the average of this deviation from the mean. So how do we get the average deviation from the mean? To calculate for the average or for the mean, we add these deviations. So we add the negative 2, negative 1, 0, 1, and 2, and then divide it by n to get the average deviation from the mean. Except that when we add the deviations from the mean, the sum of the deviation from the mean is equal to 0. The sum of the deviations from the mean is equal to 0. You know why? Because we told you a while ago that the mean is like a fulcrum, is likened to a fulcrum, and that fulcrum tends to balance the beam, the set of values. If, for example, we have here a fulcrum and then a beam and the mean, this is the mean. And if, for example, we have here a value that's equal to 100, a weight equal to 100 in this weight, in this beam, we need to have 100 at the other end to be able to balance this fulcrum. To balance, I should say, the beam. And we can look at this as negative, the values, the beam, the 100 to the right, to the left, I should say, is negative, and the value to the right as positive. And then when we add these values, the fulcrum, the mean will be, the fulcrum will be equal to 0. And so when we add the deviations from the mean, the sum of the deviations from the mean is equal to 0. And that's also the reason why if we, for example, step on a weighing scale and you weigh, for example, 60 kilograms, you need to put the weight in the bar at 60 to balance that beam. And so the sum of the deviations from the mean is equal to 0. And because the sum of the deviations from the mean is equal to 0, we cannot get the average deviation from the mean. And so to get the average deviation from the mean, we then square the deviations from the mean and then add the squared deviations from the mean and then divide the sum by the number of deviations. So if we square -2, all of this we square, and then we have 4 negative values become positive. We square -1, and that is 1. We square 0, and 0 still -1, plus 1, we square that as 1, and 4, and 2, we square that becomes 4. And then we can add, we call this actually the squared deviations from the mean. Squared deviation from the mean. And so we can add the squared deviation from the mean, and that should be equal to 10. So when we add, this is called the sum of the squared deviations from the mean. And then we can get the average when we divide that by 2. When we divide this by 2, by 5 I should say, the sum, the average squared deviation from the mean is equal to 2. So when we divide the sum of the square deviation from the mean by n, we have the average square deviation from the mean equal to 2. Actually, the 2, which is what we call the average square deviation from the mean, is what we call the variance. We call this the variance. So I have 5 patients whose ages are 1, 2, 3, 4, and 5. And the mean age of my 5 patients is 3 years old. 3 years old. And the variance is 2. The variance is 2. And the unit is years squared. Because we squared the deviations from the mean. And so the unit of the variance is in squares. So we say that the variance is 2 years squared. But really, 2 years squared doesn't mean anything. We cannot conceptualize 2 years squared. What does that mean? It doesn't mean anything. We need to bring this back to its original unit. And the original unit is years. So to bring this back to the original unit, we need to get the square root of the variance. And the square root of the variance is what we call the standard deviation. And so, when we get the square root of 2, that is equal to 1.14. And that's the standard deviation. 1.41, I am not sure now. Anyway, you get the square root of 2, and that's actually the standard deviation. And we told you that the standard deviation is the deviation, the average deviation from the mean, conceptually. But prior to that, let me just tell you that the variance is defined as the average square deviation from the mean. Because we square the deviation, we explained this to you a while ago, and just to repeat, just to read to you, because we square the deviations from the mean, the unit of measurement for the variance is squared. And to go back to the original unit, we get the square root of the variance, and the result is the standard deviation. So the square root of the variance is what we call the standard deviation. So just going back to the standard deviation, we have here the roots, different travel times for root A and for root B. The mean is 30 in both roots, and the standard deviation for root A is 18, and the standard deviation for root B is 2.6. You will note that the standard deviation in root A, there is much variability, is much higher in root A than in root B. There is less variability in root B. Now, the process of computation of the standard deviation really helped us to clarify its meaning. So, as we told you, the standard deviation is first computed by taking the deviations of its value from the mean, and we denoted each value by an x. So, this one, x minus mu. And then, but we have two important properties of the deviations from the mean. The first important property is that the sum property, the zero sum property, which means that the sum of the deviations from the mean is equal to 0. And then the second property is what we call the least squared property, which I will explain in a little while. And that means that the sum of the square deviations from the mean is lowest among sums of square deviations from any values, from any other values other than the mean. So if we get the square deviations from other values other than the mean, the sum of the square deviations from the mean is lowest. We call that actually the least squared property. And because of that zero sum property, we told you that that the deviations from the mean will yield positive and negative values, And these deviations have to be summarized as our average. But to get the average, we add the deviations. And again, we told you that when you add the deviations, the sum is equal to 0. We explained this to you. And so we cannot take the average deviation from the mean. To get away from the zero sum property, we square the deviations, add all the square deviations, and then divide the sum by the number of deviations. We explained that to you a while ago. And then the result is what we call the variance. The variance is defined as the average square deviation from the mean, and then it is squared. And then in our example, the variance is reported as minute square. To go back to its original unit, we get the square root of the variance, and the result is the standard deviation. And so here, our example a while ago, so these values are called the deviations from the mean. So the mean is 30, 12 minus 30 is negative 18, 13 minus 30 is negative 17. In much the same way, the mean is 30 for root b, 25 minus 30 is negative 5, 28 minus 30 is negative 2, and so on and so forth. So we call this the deviations from the mean, and if we add the deviations from the mean, the sum is equal to 0. Much the same way, if we add the deviations from the mean for root b, the sum is equal to 0. And then we square the deviations from the mean. When we square 18, we have this value. 17, we have these values, and these are called the squared deviations from the mean. And for root b, these are called the square deviations from the mean. And then the sum, we add the square deviations from the mean, and then the sum is called the sum of the square deviations from the mean here in root a and in root b. And then we divide the sum of the square deviations from the mean by n, by 10. And then this is the result in minutes squared. This is called the variance, and it is denoted as sigma squared. This is called the variance. And the variance for root b is 6.6 minutes squared. And then if we get the square root of the variance, we have the standard deviation equal to 18 minutes, denoted as sigma for root a, and then 2.6 standard deviation for root b, denoted as sigma for root b. And by now, we would have known the formula for the variance. So the formula is getting first the deviation from the mean, and then squaring the deviations from the mean, and then adding the deviations, the square deviation from the mean. So we have this notation, sum of the squared deviation, sum of the square deviation in from the mean, and then we divide it by n. And so we call this the average square deviation from the mean, called the variance. And then when we get the standard deviation, we get the square root of this variance. This is called the standard deviation. We have what we call, many years ago, a computational formula for the variance. We did this many years ago when there was no computers yet, and calculating for the variance and the standard deviation is rather difficult. And so we have what we call the computational formula, which is this one for the variance, and this is actually the sum of x squared, you square the x's, so you square each of the values, and then we add all the values, so we call this the sum of x squared. And this one is sum of x and then you square the sum of x, meaning you add all the x's, and then you add all the x's, that sum of x, and then you square the sum. And the formula is sum of x squared minus the square of the sum of x divided by n, 1 divide this by n, and then we divide this is your numerator divided by the denominator, and that is the variance. And then we get the standard, the square root of this one, that's your standard deviation. But of course, now in the with our computers, we don't need this formula anymore, because really we can calculate the variance and the standard deviation very, very quickly with computers. Now, we told you that there is another measure of dispersion which I didn't write a while ago, the coefficient of variation. That's a single statistic that combines both the mean and the standard deviation. It provides to us a measure of the standard deviation relative to the mean, and it is particularly useful when comparing the variables of comparing the variability of different units, variables of different units or categories. So let's give an example. Suppose we want to compare what is more variable, weight in kilograms and height in centimeters. We have here weight in kilograms whose mean weight is 50 and the standard deviation is 3.9, and height in centimeters, the mean weight is 160 centimeters and the standard deviation is 7.5. Now, what do you think has more variability? Weight in kilograms or weight or height in centimeters? We told you that to look into the variability, which has more variability, we look at the standard deviation. And if the standard deviation is high, there is more variability in that set of value. So in this particular example, it seems to us that height in centimeters is more variable than weight in kilograms, because this has higher standard deviation than the weight. But of course, we cannot tell because we have different units, one in kilograms and one in centimeters. But even if we have the same units, for example, you want to look into compare the weight among adults, compare the variability of weight among adults and weight among infants. Adults' weight, mean weight is 45, the standard deviation is 2.9. Infants' weight is 5, the standard deviation is 0.69. Again, if we were asked which has more variability, adults' weight or infants' weight, so it seems that there is more variability among the adults' weight because the standard deviation 2.9 is much higher than the standard deviation in the infants 0.69. But then again, we cannot really tell because though we have the same units in kilograms, we have different categories. One, adults, another one, infants. In these two examples, in both situations, it is difficult to decide which has more variability. And the coefficient of variation becomes an important tool. And it is defined as the ratio of the standard deviation to its mean expressed in percentage. Standard deviation divided by the mean times 100. And that is your coefficient of variation. And so we will use the coefficient of variation to compare the variability for the example of the data that we gave you above. So the coefficient of variation for weight in kilograms is equal to the standard deviation divided by 50 times 100, and that's equal to 7.8. And for height in centimeters, this is the standard deviation 7.5 divided by 160, the mean, and 4.7 is the coefficient of variation. Now, if you look at the coefficient of variation, we will note now that height in centimeters is more variable than weight in kilograms. A while ago, we thought it was the weight in kilograms that has more variability than height in centimeters. Now, we look at the weight among adults and infants. And so, for adults, the standard deviation is 2.9, and this is the mean, 45 times 100, and the coefficient of variation is 6.4. For infants, 0.69 is the standard deviation divided by the mean, 5, and the times 100, we have the coefficient of variation equal to 13.8. From this example, we note that infant's weight has more variability than adult's weight. A while ago, we thought adult's weight has more variability because it has higher standard deviation, 2.9, than the infant's weight, 0.69. But really, infant's weight has higher variability from the coefficient of variation. And so, using the coefficient of variation, we find the weight to be more variable than height in centimeters, and weight among infants more variable than weight among adults. Now, up to this point, we have pretended, and I would like to emphasize this word, pretended, that the data we take are population values. But really, class, in reality, we rarely observe population values, or we do not observe population values. They are, in fact, more often than not, unobservable because we cannot observe them. The reality is that we only take a sample of the population and observe the data, and we call this data the sample population. In practically all researches, we do not measure the whole population. We only measure a sample. And that is why population values are normally unknown, because they are not observable. We cannot observe them. If, for example, our population is people with hypertension, and then if we calculate the proportion of people with hypertension in the world, we don't normally, or even in the Philippines, just look at the Philippines, we don't normally get all patients in the Philippines and then ask them whether they have hypertension or not. We just get a sample. And so the population values, if we measure the whole population, we call this population values. But we normally do not observe population values. We only get a sample. Observe that sample. And so, I told you that we pretended that we took population values. But the reality, as I said, is that we do not observe population values. And values that we measure, if we were to measure population values, we call this the parameters. And the values that we measure in the sample are called statistics or estimates. We told you that the parameter or the values that we measure in the population, the parameters are more often than not unknown. We do not know the parameter. These are the values in the population precisely because we do not measure them. And for us to know, but we need to know the parameter. We need to know the values of the population, the parameter. And for us to know the values of the parameter, we estimate the values of the parameter by getting a sample. And we call these measures statistics or estimates. Now, the mean, the variance, the standard deviation have different symbols and even formulas depending on whether we are dealing with population values, parameters, or with sample values, estimates, or statistics. And this table actually will summarize to you everything that we have discussed about population values and sample values. So this is the population, this is the population, this is the sample. And the values that we measure in the sample are called parameters. And the values that we measure in the sample are called estimates or statistics. And these are the measures, the mean, the variance, and the standard deviation. And the symbol for the mean, if it were a population value, a parameter is mu. And that's the reason why I told you that, if we just go back to my previous slide, I told you that we pretended that we measure population values. That's why I used mu. I used mu. And the formula is sum of x divided by n. But if we only measure a sample, we call this the mean, and then the symbol is x bar, not mu. I didn't use x bar. I used mu because I said that I pretended that I measure population values. But the formula, but really if we only measure a sample, really the symbol should be an x bar. And then the formula is the same, sum of x divided by n. Sum of x divided by n. The same formula as the mu. The same formula as the mu. X bar and the mu have the same formula. Now, we look at the variance. And the variance has the symbol sigma squared. This is the symbol that I used a while ago. And this is the formula. We showed to you this formula a while ago. Sum of the squared deviations from the mean divided by n, and this is the average of the square deviation from the mean. We discussed this formula to you. And then look at the symbol for the sample. Look at the symbol for the sample. Sample variance, s squared. And then the formula is, look at the numerator, sum of x minus x bar. No longer x minus mu, and then the square. So sum of the deviations from the x bar. Square deviations from the x bar. And look at the denominator. N less 1. N less 1. You might ask, why is the denominator n less 1 here for the variance? A while ago, when we talked about the variance, the denominator is n because we want to get the average square deviation from the mean. But why is the denominator for the sample variance n less 1? This actually, people call it as an unbiased estimate of the sample variance. You see, the explanation is a little bit difficult to understand, but I'll try. This has something to do with the least squared property. With the least squared property. We told you that the sum of the square deviations from the mean is the least than among all squared deviations from other values other than the mean. Suppose I get in a finite population, for example, a finite population of 1,000 people. 1,000 students in a class. And I would like to get the mean weight of this finite population where n is equal to 1,000. And I will get the mean weight. Suppose the mean weight of my 1,000 students is 57.3 kilograms. Now, suppose I will get a sample of 50 students from this 1,000 students. So I get a sample at random using a probability sampling methodology, simple random sampling, for example, and then I get the weight of these 50 students, and then get the mean weight of the 50 students. Do you think that I will be able to get the same mean weight? We told you that the mean weight, population mean weight is 57.3, and then if I get a number of 50 students, do you think that I can get the mean weight exactly equal to 57.3? Chances are I won't. Chances are I won't. But the mean weight of the 50 students will be close to 57.3. It can be 55.2, or it can be 59.7, etc. It can be any values, but not exactly 57. Any values close to 57.3, but very, very rarely, in a very, very rare instance, can I get a value exactly equal to 57.3. And so, if I get the standard deviation, if I calculate the standard deviation of the values from the sample value, I will use the mean weight of the 50 students as my deviation from the mean. So, one value, for example, and I denote that as x minus x bar. So, x minus, for example, if the mean weight of the 50 students is 55.2, so x minus 55.2. And then another one, x minus, another value, x minus 55.2. But really, class, the actual mean is not 55.2, but the actual mean is 57.3 if we get the mean from the population values. And therefore, if we square deviations, x minus 55.2, we square all of these deviations from 55.2, and then we add the squared deviations, and then we divide it by 50. The sum, or the average deviation from the squared, the average squared deviation from 55.2 will be much higher than if I will get x minus the deviation from the actual mean, x minus 57.3. If I were to use 57.3, that's the actual mean weight of the population, the average squared deviation using the deviation from the squared deviation from 55.2, which is not the actual mean, will be much higher than if we get the sum of the square deviation from the true mean, 57.3. And so the sample standard deviation will be much higher than the actual population standard deviation. So to bring this, to lower this, because it's much higher, to lower this sample standard deviation, we divide the sum of the deviation from the sample mean by n less 1. We deduct 1 from n, and we have a much lower n, and if we have a much lower denominator, the standard deviation will tend to be much higher a little bit. And so, as I said, if we divide the deviations from the square deviations from the mean by n less 1, this now becomes an unbiased estimate of the sample variance. I told you it's a little bit difficult to understand, but if you listen closely, you'd be able to understand. That's actually the meaning of the second property, the least squared property. And again, the standard deviation, just get the square root of the variance, population variance, and look at the symbol for the standard deviation as we just get the square root of the sample variance to get the standard deviation. Now, if you didn't understand, why do we need to deduct 1 from n here in the sample variance and in the sample standard deviation? That's not really very important. It's just nice to know. But you must understand that in the sample variance or in the sample standard deviation, you actually divide the denominator with, you actually deduct 1 from n in the denominator. And if you look at the formula, if you want to get the sample standard deviation using your calculators, we have different formula for the population standard deviation and population and sample standard deviation. And I hope that's the end of my lecture on the measures of central tendency and dispersion, and I hope you're able to understand. And thank you for listening.